calculating forces due to, calculating forces when I have collisions between an object and, say, a wall or whatever, like we did. And then we'll also see conservation of momentum, which we'll get into today. So let's go ahead and try this question. I have a half a kilogram football. It's thrown towards the east at a certain speed. A guy catches it, brings it to rest in a certain amount of time. What is the magnitude of the acceleration of the ball? A couple ways you could do this. I'll show you both in just a second. Remember here we're looking at our force is dp dt, or the change in momentum over the change in time. Or as I said, there are a couple of different ways to work through this. We'll look at it first in terms of that. About 20 more seconds, yeah. Stop at 3 minutes. About more seconds. Want to click it? Okay, good. D is the right answer. The easiest way to do this is just to say my acceleration is defined as dv dt, my change in velocity over the change in time, and then the initial velocity is equal to plus 10, because it's 10 meters per second to the east, that's positive, and my final velocity is 0, so my dv is going to be 0 minus 10 divided by my time, which is 0.04, which is 250 meters per second squared. All right, or we can take the momentum route, which, remember, these are linked because momentum assumes this definition for acceleration. So I can say that my force is the change in momentum over the change in time. That's mvf minus mvi divided by my time. This mvf goes away because vf is equal to 0. So that's negative the mass, 0.5 kilograms, times VI, which is 10, over 0.04. And that gives us the force. I don't know if y'all did it this way. So this is the more complicated way. I want to show you because you need to know how to be able to calculate the force in a collision like this. That's 5 over 0.04, 0.2. That's not right. 125. Sorry. 125 newtons. And then if we want to know the acceleration, we can say that it's F over m. That is 125 newtons over a half a kilogram, which is 250. It's actually negative 125. The acceleration is in the negative direction. If my ball is traveling in the positive direction, I have to exert a force in the negative direction to make it stop. Okay, so negative 250. Okay, be prepared to calculate the force. As I said, this is the more difficult way. It was a lot easier just to do it this way, but make sure that given an object that changes its velocity, that you can find the force that causes that change in velocity. And this is just related by this, the force is change in momentum over change in time. And this is just Newton's second law, right? That's how Newton wrote his second law. So those are closely related, or they're the same basically. All right. The main type of problem in this chapter is a conservation of momentum problem. That is, when I have two or more particles collide, we can describe how their momentum changes, or rather how their momentum doesn't change. Conservation momentum is like the conservation of energy in that my initial momentum is going to equal my final momentum. So it just simply says that the momentum of the particles is conserved. That is just to say that Pi is equal to Pf. It's different from the conservation of energy because, well, what is the difference between momentum and energy and the types of values that they are, the types of quantities that they are, between momentum and energy? One is what and the other is a what? Right, so momentum is a vector and energy is a scalar. Right, so that'll treat how we are cause how we treat those problems to be different. Let's just work through an example. We'll work through several examples and we'll see different types and different levels. I'll show you what you should probably expect on your test. Let's just do a simple one first. I have two particles that collide and they rebound, and this is just in one dimension. Now on your test you're likely to have a two-dimensional problem, but it'll work out very much the same way. It's just a little bit different. I have these two particles that collide and rebound. There are their masses, 3 and 4 kilograms. There's their initial velocities. This one is moving to the right at 1 meter per second, and the other one's moving to the left at negative 2 meters per second. And then I measure the velocity of the first particle to be negative 5 meters per second, and I want to know what is V2F equal to. All right, so I have this collision, and I want to know what is this velocity. I can write in the values here. This is 1 meter per second. This is negative 2 meters per second. I'm being very careful here to keep the signs because these are vector quantities and those signs represent the directions. And then this is negative 5 meters per second. I want to know the final velocity of the second particle. So I'm just going to say that the initial momentum equals the final momentum. When I talk about the initial and final momentum, I'm referring to the total momentum of the system. So I have to take into consideration every particle, and I take the sum of all those momenta. Each particle has its own momentum, but I just add them all up, and then the sum is going to remain the same. All right. So these momenta are the sum of the momentum for each particle. In the system that we've defined. And in this system, it's very simple, right? It's just two particles, right? So it's just the sum of the momentum for each particle. So that's going to be M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And I'm looking for V2 final, so I can just solve this for V2 final. All divided by M2. And then I can put in my numbers. I had M1 was 3. I'm going to leave the units off here. V1 initial is 1 plus 4 kilograms. V2 initial was -2 minus M1, which is 1 times -5. All divided by M2, which was 4. So that's 3 minus 8 plus 5. Oh, so what is it? The velocity, final velocity. It's going to be 0 meters per second. Yeah. 3 plus 5 over here is 8 minus 8 divided by 4. M1 is 2 kilograms. M1 is 3. Did I get it? Oh, yeah, okay. All right. This is a 3 right here. Minus, sorry about that, 3 times -5. Let's see, so that's 3 minus 8 plus 15 divided by 4. -5, 10 over 4, 5 over 2, yeah, 2.5. All right. That's a one-dimensional problem. We'll see a problem in 2 dimensions. That's more likely what you'll have. Or you could have a problem where we are taking the momentum and the energy into consideration. Or you could see both. We'll see both of those in just a bit. Let's do another of these one-dimensional problems. This is a problem from the movie Dodgeball. Have y'all seen that movie? About the 2 teams that are playing dodgeball. It has that guy in it. What's his name? Will Ferrell, yeah. And this is one of the final scenes in the movie. I'm sorry if you've seen it. Have you not seen it? Have y'all seen it? Dodgeball. Well, in the end, they're sort of had this dodgeball death match, and there are 2 guys, Peter LaFleur and White Goodman. And Peter LaFleur is like the good guy, and White Goodman's the bad guy. Isn't that right? Yeah. Anyway, they sort of had this very Matrix-esque type scene where he throws this dodgeball at him and knocks this guy back. And I want to know, we'll make some assumptions about what happens here, but what is the velocity of the ball that he throws him with? And so we'll need to figure out what is the final velocity of the guy that's knocked back. But first, let's just watch the clip, and then we'll talk about it. What are the bodies involved in the system? So what are the bodies involved in a system where we have this collision? There are 2 of them. What are they? Okay, the ball and what's it? And his face, or his whole body, right? His whole body moves. So we'll look at the ball, and in fact, Peter LaFleur is irrelevant to the problem. So we're in our system. We just have the ball, which has some initial velocity. We don't know what it is, and White Goodman, who his initial velocity is equal to 0, and then in the second state, we have the ball, whose final velocity is actually equal to 0. And we see that in the movie, actually, the ball doesn't bounce off of him, but it just drops straight down, which is interesting in itself. And then you have the guy, White Goodman, who goes backwards. And we need to find out what is his final velocity. Now, how far does he go back roughly in the clip? I don't know, 2 meters, 20 meters, 5 meters? What do you think? Okay, that's 15 foot. That's pretty far. I would say about 2 meters. So we're going to say about 2 meters in about a second. So his final velocity is roughly going to be 2 meters per second. That might not be entirely right, but it's not 0.2 meters per second, and it's not 20 meters per second. So it's a pretty good estimate, I think. And then we want to find the velocity of the ball. We also need to make some estimates about the ball and the mass of White Goodman. Dodgeball is roughly how much mass, you think? A kilogram? How many pounds is a dodgeball? Maybe a pound. So a kilogram is how many pounds? About 2, yeah, a little more than 2. So if it's about a pound, that's about a half a kilogram. And White Goodman, he's a pretty big guy. I mean, he's not real tall, but he's, so 100 kilograms maybe? 70 kilograms is kind of a smallish person, so about 100 kilograms. And now we can find his final velocity. So we just say that the initial momentum equals the final momentum. In the initial state, the momentum of White Goodman is equal to 0, so I'll just leave it out completely. But the initial momentum of the ball is just going to be the mass of the ball times VI. And then that's going to equal the momentum of White Goodman. So that would be the mass of White Goodman times his final velocity. And remember, I'm leaving out this momentum because it's equal to 0. So normally I would have 2 additional terms on each side, but those are 0 in these cases. And then I can solve for VI, to be the mass of White Goodman, his final velocity divided by the mass of the ball, which is equal to 100 kilograms, 2 meters per second, divided by the mass of the ball, which is a half. It's 400 meters per second. Just to give you a little reference, the muzzle velocity of a handgun is about 300 meters per second. So this dodgeball has got some serious heat coming off of it, about 400 meters per second. Let's try another problem. This one's a little more realistic, where we actually solve, let's give it sort of a regular velocity, and there's our mass and our mass of White Goodman, and I want to know what is the final velocity of White Goodman. So if I just threw a regular dodgeball at this guy, how fast would he recoil at? So I'll give you, it works the same way, very similar, except your unknowns are a little bit different. When you get your answer, go ahead and click it in. for about 15, 20 more seconds. Pretty good. I'm going to stop at 205. What's that? Oh, okay. 205 I'll stop. I'll go to 210. Well, I think this is everybody. Okay, very good. We work it exactly the same way, right? We take the momentum of the ball should equal the momentum of White-Goodman. Because, well, actually, we have these additional terms that are included here, but we don't write them because both of these go to 0. They're equal to 0 because their velocities are 0. And the momentum of the ball is a half a kilogram times its velocity, which was 10 meters per second, equals to 100 kilograms times his final velocity, and then we find his final velocity is 5 over 100, or 0.05 meters per second. All right, so much more realistic. In fact, if you ever played dodgeball and you get hit, right, you don't go flying back, unless you're like against Peter LaFleur. He's like super dodgeball player. All right, let's try another problem. And this is more like what you'll see on your exam. It's basically the same, except now we're dealing with collisions in 2 or 3 dimensions. But you really deal with them in pretty much the same way, except you just keep all the dimensions separate. Keep your vectors in vector notation. So when I have collisions that occur in 2 or 3 dimensions, momentum is still conserved, but we can also say that momentum is conserved in the x, y, or z directions. So if I have a certain amount of momentum that's in the x direction, then I'm going to have that same amount of momentum in the x direction in the final state after the collision. I'll have the same amount of momentum in the y direction or the j direction in the final state, and the same for the z direction. So let's just work through an example. Let's see, it's on the next page. I have this collision of these particles. I have m1 colliding with m2, and I give you their velocities there in vector notation. I could also give you their velocities in at an angle, like a magnitude and a direction for the velocity, in which case you would need to write them in vector notation like this. It makes working the problem a lot easier if you write it in vector notation. And then after the collision, I give you the final velocity of one of the particles, and then I just want to know what is the final velocity of the second particle. So I do it just like I did before, where I have my initial momentum equal to the final momentum. And so this is also going to equal to m1 v1f plus m2 v2f. So these are vector quantities. And then I just want to put in my vectors. So I'm going to go ahead and put in some numbers, and then we'll see how the vectors are affected. So I have 2 kilograms times v1I, which is 4I minus 1j, plus m2, which is 4 kilograms, times negative 1I, and then that's equal to 2 kilograms times negative 3I minus 2j, plus m2, which was 4, times v2f. We've done this before where we solve for vectors, and here we want to solve for v2f, but when we're solving for it, we want to keep our i's and our j's all separate. All right, so we don't combine i's and j's together, but we can combine like i's. So for example, over here, I'll get an 8i right here. When I do 2 times 4i, that's equal to 8i, because I can multiply a scalar times a vector, and it just increases the magnitude of the vector. And then I get here a negative 4i, so I have 8i and negative 4i. So I can combine those to give me just positive 4i. 8i minus 4i is equal to 4i. Let's get that over here. All right, so I can solve for that V2F. I have 8i. I'm just going to sort of expand those. I have 8i minus 2j plus a negative 4i, or negative 4i, equals to negative 6i minus 4j plus 2 V2F. All right, now I solve for V2F. Was it 4? Oh, you're right. Here are my notes. Fix that. All right, so that's 8i minus 4i is equal to 4i minus 2j. And then I'm going to take these terms and bring them over, plus 6i plus 4j. I'm just adding those to both sides to get rid of them, equals to 4 V2F, but I just divide both sides by 4, and I get the expression for V2F. And then I just simplify it a little bit more. I have 4i plus 6i is 10i plus 2j. Both of these are divided by 4. That's equal to V2F. And so V2F is 2.5i plus 1/2 j, or 0.5 j. That's in meters per second. All right. So that's how you'd work with a collision in 2 or 3 dimensions. If you had a third dimension, you would just have a k term floating around there, and you would have to simplify it, bring all of your i's, all of your j's, and all of your k terms together, and solve for whatever vector you're looking for. As I said, if the vectors are given with magnitude and direction, you would just find out the x and y components and write those in terms of your x and y components. Let's why don't we go ahead and do this quick test, and then we might do some more clicker questions. So you'll go and practice this. I have two particles that collide. It says that after the collision, the second particle, that's M2, travels a 0.5 meter per second in the positive x direction. So that would be 0.5i, positive 0.5i as its final velocity. And I want to know, what is the final velocity of the particle M1? And just give your answer in vector notation. So exactly like we were at the previous problem. I'll give you a few minutes to get a head start, and then I'll start on it on the board. Set your initial equal to your final momentum. Does anybody have an answer yet? What is it? Huh? Is that what y'all got? 2I minus 4j? Yeah? Good. Alright, so let's see. I just say my initial momentum equals final momentum. Initially, this object's not moving, so the initial momentum is just going to be this mass times this velocity. That's 2 times 3I minus 4j. I'm going to go ahead and expand that out, okay? So it's going to be 2 times 3, which is 6I, minus, or plus 2 times negative 4, minus 8j. So that's my initial momentum of the system, and it's going to equal to the momentum of object number 1. That's going to be 2 kilograms, the mass, times the final velocity of object 1, which I don't know. That's v1f, plus 4 kilograms, times the final velocity of particle 1, which is 0.5I. Alright, so I have 6I minus 8j minus 2I minus 2I. That's just subtracting this term from both sides. Divided by 2 equals v1f. That's going to be 4I minus 8j, which is 2I minus 4j when I divide by 2. That's what y'all said? 2I minus 4j? Yeah. Alright, that's not too bad, right? Alright, there's one more complication where the algebra gets a little complicated. And we'll probably, I don't know if we'll get to that today. But let's look at different types of collisions. Actually, why don't we spend a few minutes doing some of the clicker questions first. And then maybe we'll pick up with elastic and inelastic next time. Chapter 6. We haven't done any of these, have we? No. They're in the back of your book on page... What page are they on? 293. Okay, so here we have an open cart. It rolls along a frictionless track while it's raining. As it rolls, what happens to the speed of the cart as the rain collects in it? And we assume that the rain falls vertically into the cart. I'll tell you why in just a minute. Alright, let me tell you why now. The rain falls vertically into the cart. That is, it doesn't fall horizontally, because if it fell horizontally, it would actually push the cart forward. So we're not imparting any forces to it from the rain. What will happen to this object as rain collects into it? About 5 more seconds. I'll stop at 55. Okay, C is right. Usually, oh, never mind, excuse me. We know that P is equal to mv. If our P remains constant and our mass increases, that means that our velocity has to go down. Right? So the mass is increasing, but our momentum of the system is remaining constant, and so our speed is going to go down. A system of particles is known to have a total kinetic energy of 0. What can you say about the total momentum of the system? I think we've had this problem before, or this question. Alright, I'll stop at 45. Very good. system of particles is known to have a total momentum of 0, does it necessarily follow that the total kinetic energy of the system is also 0? Oh, on the previous one, I'm sorry, those of you didn't get it right. So if the kinetic energy of the particles is 0, that means that the velocity of all the particles is 0. If a system has 0 kinetic energy, that means nothing is moving. And that's why the momentum of that system has to be 0. Now in this question, the system has a total momentum of 0. Remember, momentum is a vector quantity. So does it follow that the kinetic energy is also 0? A, yes, or B, no? Now remember, kinetic energy is a scalar quantity. Okay, so it doesn't have any direction attached to it. So to say that the system has 0 energy, they all have to be not moving. But with momentum, it's a vector quantity. So I can have two particles that have 0 momentum if they're traveling in opposite directions, because then I would have two particles with equal but opposite momenta, and so those momenta would cancel out. All right, just a couple more seconds, I'll stop. Okay, B is the right answer here. If the momentum is 0, you could have two particles that have identical masses and equal and opposite velocities, and then the momentum of this particle would equal the negative of the momentum of that particle, giving a net momentum equal to 0. But the kinetic energy of the system would not be 0 because they're moving. Two objects are known to have the same momentum. Do they necessarily have the same kinetic energy? Just a few more seconds. Stop at 25. B is right. P is equal to mv. Okay, so an object can have a velocity different from another object as long as its mass is, or excuse me, they can have the same momentum but with different velocities if their masses are different. So for example, let's say that I have an object with 2 kilograms of mass traveling at 3 meters per second. I could also have an object with 1 kilogram traveling at 6 meters per second. Right. And those two objects would have the same momentum. However, kinetic energy is 1/2 mv squared. Okay. And so these, for example, because it's a quadratic relationship with the v, they would have 1/2 of 2 kilograms times 3 squared. That's equal to 9 joules. Or they would have 1/2 of 1 kilogram times 6 meters per second squared, which will be 18 joules. Okay, so they have the same momenta, but they have different energies. You with me on this? Yeah? All right. A force acts on a 100 kilogram boulder, and a force of the same magnitude acts on a 130 gram bevel. What is the rate of the change of the boulder's momentum compared to the rate of change of the pebble's momentum? Same force acting on these two very different bodies. How do their rates of change and momentum compare? I'll stop at 115. 115. C is the right answer here. Let me show you. It's really a matter of knowing what rate of change in momentum is. We know that F is equal to delta P over delta T. And what does it mean to say a rate of change of something? Like if we were to give the rate of change in variables, what would we say? The rate of change in momentum. What is that in an equation form? It's what? It's not just the change in momentum, which would be delta P, right? Delta P is the change in momentum, but it's the rate of change. And what is a rate of change? How does it change over time? Right, so like a rate of change of displacement would be velocity, right? Delta x over delta t. And so our rate of change in momentum is delta p over delta t. And so since these both have the same force acting upon them, then they're going to both have the same rate of change in momentum. Now one of them's going to be going faster than the other, right? Which is it? Will go faster? The pebble, right? It has less inertia, and it has a force acting on it, so have a greater acceleration, and so it'll go a greater velocity. But they're going to experience the same rate of change in momentum. Let's try this one then. We'll just do a couple more. I'm going to stop at 35. Okay. We're all thoroughly confused now. Okay, the boulder, here we're talking about the rate of change of the velocity. And that refers to the object's what? A rate of change of velocity. Acceleration, right. So we can say that F equals ma. They both have the same force, right? They both have the same force, but the boulder has a much bigger mass, and so it has a smaller acceleration. So the boulder's velocity is, or the boulder's acceleration is less than the pebble's acceleration. Let's just do one more. Actually, no, we'll stop there. We'll come back to this one. So let's stop there. Next time we're going to finish this chapter on Wednesday, and that'll give you all the whole week, the whole break to sort of assimilate stuff. When we come back, we will have that one Monday. We're likely to go ahead and begin rotation. Of course, we'll spend some time on whatever you need in the class when we come back, but we'll likely go ahead and start rotation when we come back from the break, but that won't be on the exam. Just energy, work and energy, and momentum will be on the exam 1 week from Wednesday.
Next Wednesday will be our exam.
Right, not this Wednesday, not next class period, but 1 week from this Wednesday. The Wednesday after we return from fall break. Now be prepared for that exam. It should, I won't say it's easy, but it's going to be an easier exam. So I want y'all to all do as well as you can, because some of y'all didn't do so great on that last exam, and I want to try to get your average up as much as possible, okay?